Now we will talk about how to find the particular solution form. Okay, so you know that in general y, the general solution by x will be equals to the homogeneous part plus the particular part. And we already solved different scenarios regarding the homogeneous part. For example, the forcing function is equals to 0. We call it homogeneous linear ODE form. And we use that form to solve the homogeneous solution. For constant coefficient, the solution form look like e to the x. For the Wheeler-Corsi equations, we just solve, which is on the form of x to the m power. And now we will go to the particular form where the Rx is now to 0 anymore. And we know that this shouldn't have any artificial coefficient constant, but this one will have an arbitrary constant. So how we solve the particular form, we will introduce two different methods. One is called undetermined coefficient. The other is called variation of parameters. And we will use examples to show how we use these two methods to solve the particular solution form. Okay, so that is undetermined coefficient. And that is yearly. So there is a condition to use this form. Yearly, the forcing function is a simple function form. And constant coefficient. So when I say simple function with constant coefficient, I have several examples. For example, simple function can be exponential function, e to the x. It can be sine or cosine x. That is simple form. And polynomials, that is also simple form. And the constant or the coefficients aligned with these functions are constants. So it can be A, B, C, something as their constant coefficients. Another method called variation of parameters. And this is a more general method to solve the particular solution, but it's very difficult to solve it. So it's a more general form, but difficult to solve. And we will introduce two different examples using these two methods. And we will introduce the undetermined coefficient first. So we will make our example is a second order linear ODE. So it's y double prime plus p x y prime plus q x y equals to a forcing function Rx. And you know that a coefficient is all as function of x or constant, and the forcing function as well, so that this is a linear higher order ODEs. And we are trying to solve the YP part, okay, using the undetermined coefficient. So you see, there are several rules how you solve the undetermined coefficient. We will talk about first is the general rule. The general rule is basically use solution form for the particular solution is the same format as compared to your forcing function. So that is the same form as forcing function and all is derivative. Okay, the general rule is the particular solution when your Faustin function is very simple, okay? So this is a condition. When it's very simple with constant coefficient, then you can use undetermined coefficient. The general rule for undetermined coefficient is that the particular solution form is the same format as compared to your Faustin function and all its derivatives. What's that mean? So for example, if your Faustin function is e to the x, then the solution form will look like e to the x and its derivative, which is still e to the x. When you have, for example, Faustin function is sine x, then your particular solution will be the same format as Faustin function, which is sine x, as well as its derivative, which is cosine x. So it will be a combination of sine x and cosine x. And the same as polynomial. So if your, the Faustin function is x to the second order x squared, then it will be the same format as the Faustin function for your particular solution, which is x to the second order x squared, and all its derivative will be also include x and some constants. So that is the general rule for undetermined coefficient. There is also some special rule here. So special rule. The special rule is if u by p, well, the general rule for a constant coefficient linear system contains the term that are solution to the homogeneous solution by hx, then that term will need to multiply the choice of x. Okay, so probably couldn't see. So the special rule is that if you particular solution, well, the general rule, for example, if your Faustin function is e to the x, then well, the general rule will be, the particular form will be e to the x. And if this is a constant coefficient linear ODE, for example, you will get the homogeneous solution will be still e to the x term, right? If that term are the same as what you derive from the general form, if they are the same, then the particular solution, when you solve, you need to times x, then will be x times e to the x. Similarly, you will have similar things. For example, if you have a polynomial that is the same as your homogeneous solution, you need to time the term with x. We will make examples how that works, okay? So you will be more clear what I'm talking about, this general form and the special rule, okay? So we will make an example. And this will be a second order linear ODE with constant coefficient. So y double prime plus 4y equals x squared plus 8 cosine 2x. As you see, this second order linear ODE with constant coefficients, right? Then what we can get is, first, we know that the general solution form will combine both the homogeneous part and the particular part because the Faustin function is not zero. So first, you need to find the homogeneous solution form. And in order to find the homogeneous solution form, you need to consider only the homogeneous part of this equation, which is y double prime plus 4y equals to 0. So it becomes a homogeneous ODE with linear, with constant coefficient, and you know that the solution form should be e to the x, right? So you can assume the solution form will be e to the lambda x. Then what you can get is basically you can generate the characteristic polynomials. So you assume y(x) equals to e to the lambda x. Then you can put y double prime will be lambda squared e to the lambda x. Y is e to the lambda x. Put y and y double prime with the term on the right into the original solution, which is y lambda square e to the lambda x plus 4 e to the lambda x equals to 0. Then you can get the characteristic polynomial is lambda squared plus 4 equals to 0. So your lambda will be equals to plus minus 2i. This is an imaginary number there, right? Then your homogeneous solution will be a linear combination of two linear independent solutions here, y1, y2. So it will be C1, y1 plus C2, y2. C1, y1 is e to the 2ix plus C2 will be e to the minus 2ix, right? And you also know that, so here is the part that transform the e to the x to sine and cosine function is important. So note that e to the ix will be equals to cosine x plus I sine x. Then you can get that, e to the 2ix will be equals to cosine 2x plus I sine 2x. E to the minus 2ix will be equals to cosine minus 2x will be still 2x plus I times sine minus 2x, that will be cosine 2x minus I sine 2x, okay? And you can use the cosine and the sine form to replace here the homogeneous solution. So in the end, you will have your homogeneous solution written as a constant times the cosine 2x and another constant times the sine 2x. And this constant k1, where this constant k1 with the relationship with c1, c2 is c1 plus c2, and the constant k2 will be equals to I times c1 minus c2. And in order to calculate what is this constant, you need to have either, two initial value conditions or two boundary value conditions in order to solve this arbitrary constant. Okay, then finding the particular solution